All right, so we're kind of looking at the same figures here, but I did throw the equations in. I think it'll be a good slide to reference because these equations are very important. However, I'm still going to go through this example and show how they work. But just so you have this slide on deck, if you ever need to reference how to convert from polar to Cartesian or vice versa, the equations are here. Okay, so let's go ahead and use them. So if I'm talking about this point in the XY coordinate plane, 6, 4, I know that my X value is 6 and my Y value is 4. Okay, so we're talking about, this would be the Y value here going up and the X value here going across, of course. And on the right-hand side in polar coordinates, we typically refer to this magnitude of this vector as r, right, the length of the vector, and then we refer to the angle sometimes as theta. I used phi here, or phi, whatever you want to call it. But I'll just start calling it phi. But not where I just didn't use theta. It doesn't really make a difference. But so if I wanted to convert from, this, if I wanted to figure out what is this 6, 4 in, polar coordinates, I would use these two equations right here. And so let's do the first one. So if, and you can see that this is literally just a Pythagorean theorem, like I said, for a right triangle. So r is going to be x squared. X in this case is 6. Y is 4. And if I throw this in my calculator, I get 7.211, which I can just approximate as 7.2. That's how I got this, right? And if I take the tan inverse, I want to get my angle phi here. Take the tan inverse of y over x, which in this case would be 4 over 6. I should, if I have my calculator in degrees, I should get, say my calculator is probably in radians, so let's go switch that over. Yep, put it in degrees. Radians and degrees are a big deal. Make sure you keep track of which one your calculator is in. Yep, I get 33.7 degrees when I'm in degrees mode here. So that is exactly where these two values come from, right here, right? So just to show that. And then if I wanted to go back, let's say I have the polar coordinates and I want to go to the XY coordinates, I can do exactly what I have written here. So my X would be 7.2 times the cosine of 33.7. Again, make sure you're in degrees because I'm throwing degrees in there. So let's go cosine of 33.7 and then multiply that by 7.2, and I get 5.99, which is close enough to 6. And if I do Y, of course, this would have been 6 if I put 7.21111 here, but I rounded to 7.2, so I lose some accuracy. That is okay in engineering. Get used to approximating. This is going to be part of your life now. 7.2 times the sine of 33.7, and I get 3.99, which is close enough to 4. So that is how you can convert. That is pretty ugly. That's how you can convert coordinates from Cartesian to polar and vice versa. Okay, so just wanted to throw this slide in there. I'm going to go ahead and end this video, pretty short one, but just wanted to kind of prove that these equations work. Let's throw a box around this one, a box around this one. And yeah, feel free to reference this slide whenever you need to. This is going to be common as we move into solving these circuits, that you need to translate Cartesian to polar and vice versa. A lot of calculators can do it for you, but maybe you want to do it by hand, or your calculator doesn't do it for you, then these equations are simple enough, okay? Going to go ahead and end the video now, and then in the next video, we're going to start a little bit of a review of the unit circle.